Okay, we're going to be looking at displacement as the integral of velocity with respect to time. So, we know already that the velocity is the derivative of displacement. And because the opposite of the derivative is integration, we can say that the displacement is the integral of velocity with respect to time. This also means that, say we have a velocity time graph, and say we've got some curve, the area under that curve will give us the displacement. Now let's think about the motion of some particle with respect to time. And we're going to start off at position A. And we're going to think how this motion changes. So at position B, the velocity is 0. Position C is the minimum. D, the velocity is 0 again. And this is in seconds. So the velocity starts here as positive. And initially, the velocity is decreasing, so the particle is slowing down here. However, the velocity is positive, so the displacement is increasing. The particle is moving away from its starting point. When the graph crosses the x-axis at point B, the particle has a velocity of 0 meters per second and is momentarily at rest. However, the velocity continues to decrease, but it's now negative, so it's now travelling in the opposite direction. It's going back towards where it came from. The velocity decreases to a minimum value at C, and then it starts to increase again, but it remains negative. This means the particle is continuing to travel in the negative direction towards the start point, but it is slowing down. When the graph crosses the horizontal axis at point D again, the particle is once more momentarily at rest before it changes direction. The velocity continues to increase, but is now in the positive direction. Suppose we have v equal to t squared minus 13t plus 22. We can factorise that as t minus 2, t minus 11. The graph at v equals 0, t must equal 2 or t equals 11. So b must be t equals 2 and d is t equals 11. The velocity, the particle starts, the velocity of the particle starts at with 22 meters per second. So that's at the start. For 0 less than or equal to t less than or equal to 2, the particle moves in the positive direction, and for this particle and for t between 2 and 11 is in the negative direction. For t greater than 11, it's the particle is in the positive direction again. Now, to find the displacement from the starting point, we would integrate. So S is the derivative of v dt. So it's t squared minus 13t plus 22 dt, and that will give us a third t cubed minus 13 over 2t squared plus 22t. The constant of integration is 0 because when s is 0, t is 0. So if we were to look at, we can look at put in some values for t to get some values for s. Now if we were to do a sketch of how the displacement varies, say the particle, we'll start with the particle at point A, and so s equals 0. It goes away in the positive direction and then it gets to point B, and that's at t equals 2, v equals 0, and if you were to plug the numbers into the displacement equation, s would be 20.7. Now, after this it then goes in the opposite direction, and at point C, s equals 0 because this is a minimum. So it's back at the same position. Then as it continues at point D, here, this is at t equals 11, v is 0, and if you were to put t equals 11 into this equation, s would be minus 101. And then it continues back into the positive direction. Displacement and distance travelled are not necessarily the same thing. The displacement at a time t is the position of the object from the origin at that time, but the distance travelled at time t is the sum of the distances travelled in the positive and negative direction. So, for example, if you were to look at point, is at point A, this one's going to point C, here's C. When the particle's at point C, the displacement is 0, but it's not travelled 0 meters. It's travelled along the positive direction and at the negative direction. So, for example, for t equals 3 seconds, the displacement s is 16.5. However, the object travelled 20.7 in the positive direction, and then minus 16.5, so we get to 28.7 that is travelled here, and then minus 16.5, and that's 4.2 meters in the negative direction. So the total distance, not displacement, is the initial 20.7 plus the 4.2, which is 24.9 meters. So in 3 seconds, you've got the distance to here, 20.7, and then add 4.2, and it's 24.9 metres that it's travelled. The distance travelled is the area between the curve and the horizontal axis. But in this example, the curve is below the horizontal axis and above the horizontal axis. So to find the total distance travelled, you must break the motion up into the different parts so that the displacements don't cancel each other out, and then sum the different parts of the motion so that you get the total distance travelled. Let's look at some examples. A particle moves in a straight line so that its velocity is v meters per second. At time t seconds, it's given by v equals t cubed minus 4t. Find an expression for its displacement. So we're going to integrate v equals t cubed minus 4t because s is the integral of the velocity. Oops. 4t dt. So this will be quarter t to the power 4 minus 4t squared over 2 plus c. And tidying it up, quarter of 4t minus 2t squared plus c. But s equals 0 when t equals 0, so c must equal 0. So you'll end up with as the expression for the displacement. So a particle moves in a straight line so its velocity v meters per second at time t is given by v equals t cubed minus 5t squared. Find the displacement after t equals 5 seconds. So the first step is to integrate it. So s is going to be the integral of v dt. So we'll integrate t cubed minus 5t squared dt. So it's going to be quarter t to the power 4 minus 5 over 3 t cubed. Now we want it after 5 seconds, so we're going to integrate it with between 5 and 0 seconds. So slotting the 5 into t, we'll get minus 52.1 meters. So part B of this, sketch the velocity time graph. Now, we've got v is t cubed minus 5t squared. What we're going to do is, to get a handle of the shape of this curve, we're going to factorise it. So we're going to take t cubed out, and then we'll have t minus 5. So we know at t equals 0 and t equals 5, v equals 0. I'm going to draw it up here. So t equals 0 here, v is 0, and at 5 here is 0. And because it's cubed, it's going to increase. So there's a minimum and it goes up. When you're sketching the graph, it's not an accurate picture, it's just a rough idea of the motion of what's going on. If you're feeling not confident, put a few numbers in just to look for the minimums, look for it crosses the horizontal axis, just to get an idea of the shape. I'm going to need to get another. So the final part of the, no, not the final part, work out the distance that the particle travels in the first 10 seconds. So I'm going to re-sketch our velocity time graph. This is 5 seconds. We know, we've already worked out that from the displacement, and we worked out when it was from the 0 to 5, we had, let's write this back in. We worked it out previously for the first 5 seconds that it was minus 52.08. That was in part A. So this tells us this is the displacement in this part, but we want it up to 10 seconds. So we're now thinking about the motion from 5 to 10, and we have to add the two together. We can't integrate and work out the two and work it out as from 0 to 10, because the velocity curve goes below and above the horizontal axis. So now we're going to do the integral from 5 to 10. So we've got that's 5 over 3 t cubed 5 to 10. And if you put all the numbers in, we'll get 885.42. So therefore, the total distance in the first 10 seconds is 52.08 plus 885.42, and that's going to be 938 meters. And the final part is find the time the particle passes through the start position. So that's when the displacement equals 0. So we know that the equation for displacement is this, 5/3 t cubed, and we want that to be equal to 0. So we're going to bring out a factor of a 12 t cubed. It's going to be 3t minus 20 equals 0, so t equals 0 or t equals 20 over 3. So at time t equals 6 2/3 seconds, the particle passed through the starting position. Let's do another one. A circus performer rides a unicycle along a tightrope. The tightrope is modelled as a straight horizontal line, and velocity is modelled by v equals 1 for times between 0 and t equals 2 seconds. Then the velocity changes to 2t minus 3 for times between 2 and 4 seconds, and then finally it changes to 7 minus square root of t for t between 4 seconds and some time big T. So we want to firstly find the value of t, and then calculate how far the performer cycles. So when the performer, no, put a bit of information. The performer stops at time t seconds, having come to the end of the tightrope. So, to so let's look at this. V equals 7 minus root t. At the end of the tightrope, at t equals big T, the velocity must equal 0 because the performer comes to a stop at that time. So 7 minus root t equals 0. Square root of t must equal 7, so t must equal 49 seconds. Calculate how far the performer cycles. So we're going to integrate v with respect to t. So for s equals 0, when t equals 0, s equals the integral of 1 to t, but s equals t plus c1, so this constant 1. So when s equals 0, t equals 0, so c1 equals 0, so hence s equals t. Therefore, at t equals 2 seconds, s equals 2 meters. So that's usually the first part of the first equation. Then for t between t and 4, s is going to be the integral of 2t minus 3, which will be t squared minus 3t plus some constant t2. When s equals 2, when t equals 2, so 2 equals 4 minus 3 times 2 is 6 plus c2, so c2 is going to be 4. Therefore, we've got s equal t squared minus 3t plus 4. And just put that one there. And when t equals 4 seconds, s will equal 8 meters. Now I have to get another. So we said when t equals 4 seconds, s would equal 8 meters. Now the last part, for 4 less than t less than 49, we had v equals 7 minus square root of t, so that will give us s must be integral of this, so we're going to have 7t minus 2/3 t 2/3 plus c3, when s is 8, t is 4, put this up here, this will give us 8 equals 7 times 4 minus 2/3 times 4 to the power 1.5 plus c3. c3, working all that, will be minus 14 2 over 3. Therefore, S is, on the last part of the motion, the equation for the displacement is 7t minus 2/3 t to the power 1.5 minus 14 2/3. So at t equals 49 seconds, slotting that in, we'll get a distance of 99 2/3 meters. Let's do one more. A particle moves in a straight line so its velocity is given by v equals u plus at. Find the displacement. So S is v dt. So it'll be u t plus a half a t squared plus c. But it's moving in a straight line at the when the displacement is 0, that's going to be at the start of the motion, so t is 0, so c must be 0. So what we have just derived is one of our equations of motion, which we were using way back at the start of this mechanics course. So I hope that helps.